let's continue. Part 4, lecture 4b, tensor. Example. If V is the space of three-dimensional position vectors, like, you see that the space V, okay, in R3, then V star is the space of linear functional maps like. You see, this is a map. Tensor is a map. You see, this map, okay, I have it, a vector in R3, leading to the scalar. R is a real, okay? R is a scalar. See, that's a definition of tensor. Now, this example, I have a linear combination of vector V belonging to capital V over here. You see? This is a covector or dual vector. It acts on this vector V here, okay? And this is a linear combination. So, remember that phi is a covector, or in general called dual vector, okay? Then this acts as a linear combination. Now, let's work in this space here, okay, R3, the space of the three-dimensional vectors. I'm repeating here, okay? Now, a typical vector in this space looks like, you see, there's a three-dimensional, see? There's a three-dimensional vector, okay, in this space, capital V over here. Now, you see, let's now consider a covector or a dual vector, okay, phi. In R3, you see that there are components of these covectors or dual vectors, okay, phi1, phi2, and phi3, because we are working in R3, okay? Now, this is a row vector. Why it's a row vector, okay? Because if phi acts on this vector u must lead to a scalar quantity, okay? That's the definition of tensor, okay? Now, this is a row vector, this is a column vector. If I multiply now 1 by 3, 3 by 1, this leads to 1 by 1, which is scalar, okay? This is dummy, okay? This is a scalar quantity. That's a definition, okay, of a tensor. Now, numerical example, okay? In R3, suppose the components of this dual vector is 1, minus 1, and 2. And the component of this vector is 3, 1, and 4. So I multiply, okay, this row multiplied by the column. So this will be 1 times 3 plus minus 1 times 1 plus, now 2 times 4. You see? Just this one times 3 plus minus 1 multiplied by 1 plus 2. So this will be 3. This is minus 1 plus 8 is equal 10. You see? 3, that's 10. You see, look, it's important. It's scalar. You see? So that's an example. We can extend, okay, this definition of tensor to higher order tensor. Second order tensor, third order tensor. This is just one order tensor, okay? That's the definition applied to one, in this case, one order tensor, which is a vector, okay? Now, two-order tensor, you have, for instance, the components, okay? In R3, we gave an example, okay? I call Tij, okay? But I'll extend this to a second order tensor, okay? An example, just for you to understand clearly what is a tensor. Is this definition that we will use for curvilinear coordinates. Here we don't talk about curvilinear coordinates. We don't talk about Euclidean coordinates, cylindrical coordinates, spherical coordinates. This is a general definition. General definition, tensor is a map. That's it. Okay?